Hi guys, hope things are going well and that you're staying safe. Last time we looked at Unit C, pages C1 to C4 on linear correlation. We're going to continue with that, taking a look at the hypothesis test. Let me just back up one page here to the top of page C4, right here, where we were talking about calculating Pearson's R. Remember, R is the sample statistic, which is used to estimate the population correlation coefficient rho. We ended up with an R of 0.897 down here, right there. If you didn't understand that, or go back and take a look at that first video that we had on pages C1 to C4. So this is looking at the relationship between height and weight, and it's quite a strong positive correlation. Now, at the end of the last mini lecture, I said something that I really need to clarify. I was talking about a strong relationship and then a significant relationship. There's actually a difference between the two. So when we talk about a strong relationship, we talk about something which is close to -1 or +1, whether it's a negative relationship or a positive relationship. So the closer it gets to plus or minus 1, the stronger it is. The weaker relationships, of course, are closer to 0. When we talk about significance, the question is, well, is this particular correlation significantly different from 0? Or we could test it against some other value. Is it significantly different from 0.5, which is what it was last year or something? We won't be doing that. We'll just be looking at whether it's significantly different from 0. Now, 0, of course, means that there's no relationship between the two. You can end up with an R which is quite small, like 0.1 or something like that. And actually, if you have a large enough N, such as, say, 1,000 respondents, it can actually be significantly positive, although it's not a very strong relationship. So it's significantly different from 0, significantly positive, but not a real strong relationship. So I wanted to make that distinction. I don't think I said it very well last time and led you astray. Anyways, let's get back to our problem here. So we want to take a look here at whether R is actually significantly positive in this case. We're going to use a hypothesis test here, and it's set up the same way as any hypothesis tests are set up here. So the null hypothesis down here is that rho is equal to 0. Now again, it could be that rho is equal to 0.5 and we want to test that, but we'll not do that. The null hypothesis says that there's no linear relationship between the two variables, and that means that rho is equal to 0. The alternative is that rho is positive, or it's negative, or that it's not equal to 0, so that there's some relationship, but we don't know whether it's a positive or a negative one. The test statistic that we're going to use here looks like this. So it's a T star value is equal to R minus the hypothesized rho value in the null hypothesis, which is going to be 0 in the problems that we're going to be looking at, divided by the standard error of R. And that's found down here, like so. So it's the square root of 1 minus r squared over the square root of n minus 2. Now the n minus 2 is talking about the degrees of freedom actually for this problem here. So remember when we were calculating standard deviations before, it was n minus 1 because we were only dealing with one variable. And so when we're talking about calculating standard deviation of x, you lose 1 degree of freedom for every population parameter that you have to estimate with a sample statistic. So we would use x bar instead of mu. Here, we're talking about the correlation between x and y, so you lose a degree of freedom for the mu of the x's and the mu of the y's, and have to use x bar and y bar in their places. So that's where that comes from. We can combine these two formulas here into a simpler formula that looks like that. So that's the one that we're going to be using here. The rejection region, depending on the form of the alternative hypothesis, then it is upper tail or lower tail or both, and it's n minus 2 degrees of freedom. And then we calculate the starred value, the t star value, as usual, and we make our decision and conclusion here. So just like any other hypothesis test here. All right, let's take a look then at our problem here. What page am I on? I'm on page C6, which is page 140 of your manual. So the class example was conduct a hypothesis test for the height-weight problem presented above. And again, you can take a look at that problem back in the first video. What we had here was R was equal to 0.896, and we had an N equal to 10 pairs. Remember, not 20 numbers, but 10 pairs of X's and Y's. All right, step number 1 is that rho is equal to 0. Remember, you never put down that R is equal to 0. We're never testing a sample statistic. We're always testing a population parameter. The alternative hypothesis, I'm going to say, is that rho is greater than 0. Now, a really important thing to note here, remember that we never form the alternative hypothesis based on the sample statistic. In fact, this is a two-step process. You form your hypothesis, your critical region, and your decision rule. And then there's a time lag, because then you actually go out and you gather the data and you calculate your sample statistic and then do the calculation and make the decision. So in reality, at this point, we don't even know that R is positive here. I'm saying in this particular example here that I'm hypothesizing that if there's a relationship between height and weight, I would expect it to be a positive one. So that's what we're going to look at. On an exam problem or an assignment problem, I would specifically say what the researcher is testing, whether it's positive or negative. Otherwise, it would be a two-sided test. So in this particular case, I'm saying that I believe that if there's a relationship, that it's a positive one. Now, of course, we can change the null hypothesis to less than or equal to. I'm fine with you just keeping it as equal to. I seem to have lost my page here. There we go. I'm fine with you keeping it as equals rho, as long as we understand that what we're testing is whether it's significantly positive. A negative R would actually support the null hypothesis. The test statistic is just the t star. Calculated t is equal to R times the square root of n minus 2 over the square root of 1 minus r squared. All right. Step number 3 is our decision rule. Now, this is taking a look at the classical approach where we're looking at a critical value. Let's draw it this way. So this is, that's not very good. We've got a t distribution with 8 degrees of freedom. Why 8? Well, that's n minus 2. Now, in our case, and usually I use red here for the critical region, but I've been drawing in red, so I'm just going to change colors here and say our critical region is going to be in the upper tail, because that's what the sign of the alternative hypothesis says. So we're going to have the whole alpha here. Alpha was not given, so we're going to assume an alpha of 5%. So we're looking for a t value, 5% in the upper tail, 8 degrees of freedom. I'm going to assume that you know how to look that up on a t-table. And I'm just going to check my notes here. That is a 1.86. So positive 1.86 is your critical value. So in other words, if your t star value is greater than positive 1.86, then we would reject HO. If we were to do this in Excel, then what would be the function that we would use to get the critical value? it would be a T inverse, of course, because it's a critical value. We don't have a T inverse dot RT function like we do in an F distribution or with a chi-square distribution. And so it's a T, where am I, inverse, and then we would put in 0.95. That leaves you with 5% in the upper tail, 95% from that point down, and then 8 degrees of freedom. So that is where you would get 1.86. All right. Now, I'm just going to move over here and say, if this were the p-value approach, what we would say is that if the p-value is less than alpha, which in this case would be 5%, we would reject HO. So remember, step number 3 is your decision rule. And this is the classical approach here. This is the p-value approach here. All right, now we actually take the sample. So let's go and stick the values into the formula here, and we get T star is equal to, what do we got in my notes? Positive 0.896 times the square root of 10 minus 2 over the square root of 1 minus 0.896 squared. And that comes to 5.70. Now 5.70 is way, way out in the tail. So 5.70 is right about here, 5.70. So it's way, way out there. So what we would say is we would reject HO, and that is, therefore we would conclude that there's a significant positive correlation. If you look up the p-value for this, it turns out to be really small. It's almost 0. And the way that you would find that is that's equal to a T dist function. I think there's a right tail function here. And so we would have 5.70, 8 degrees of freedom. Alternatively, you could take 1 minus the T dist, 5.708, and that would give you the area going down, and then 1 minus that. So that would give you the p-value. It's going to turn out to be pretty close to 0. So we would end up rejecting HO. All right, I'm going to end the lesson there. Next, what we're going to do is take a look at one more problem here, which is on page C7. So that will be in the next lecture. Let's end it here.